Reflection and mirrors. So the first question they ask is actually what we talked about. Is my image reversed in my bathroom, or is it just my brain? Your brain is reversing it. We're going to talk about why that is, because of how we see everybody else that faces us. And so when you start thinking about reflection and mirrors, we have a whole bunch of terms. So you're going to see a lot of terms in this section. Light is represented by a group of rays. So we all hopefully know what a ray is from geometry. You know, it has a starting point and then it goes infinitely in one direction. And that is really how we're looking at light when we see things. Light travels in reasonably straight lines. There are things that skew it. We talked about permeability of objects, and that's how quickly it's going to go through. And then shapes of objects can adjust that a little bit. But when it strikes an object, it will then reflect off of the surface. So there are multiple types we're going to talk about. The first one is diffuse reflection. Diffuse reflection. So this is the phenomenon that occurs when a rough surface reflects rays so that a clear image is not visible. All right? A rough surface is reflecting so that a clear image is not visible. All right? If you have ever seen, like even if you've looked in water, it's going to be diffused to an extent. That's also because it's not perfectly straight. But, you know, I'm sure that you have seen even a fogged mirror. You know, you've just taken a shower and you look in the mirror and you're like, oh, that's not very good, right? And it kind of diffuses the light reflecting back. So the image itself is not clear. They mentioned I thought this was really cool. The stealth fighter, which is a picture that's shown up here. It's actually designed to reflect radar waves in many directions so that it's hard for them to get a clear radar image of it. And so the way they actually made the surface of the plane itself is so that these different rays, I mean, whether it's light waves, but in this case, radar waves, radio waves, cannot reflect perfectly off of it. And so it's hard for them to then detect it because it's sending it out in all different directions versus just one. Reflection is specular reflection. This is the phenomenon that occurs when a smooth surface reflects light so that a clear image is visible. So the surface of what's reflecting itself is going to affect the image. And there are a lot of examples. I mean, like, you know, I have this little metal thing on the back of my phone. It is clearly not a perfectly reflective source. You can kind of see in it, but you can also tell that it's not a clear image. Versus your mirror in your bathroom, if it's nice and smooth, nice and clean, you're going to get a very clean image, very clear, very visible. All right? And so the first thing we're going to talk about is the law of reflection. We're going to get into these incident rays, but we have the incoming rays that come into the reflective surface is called your incident ray. This is your normal ray. And then you have a reflected ray. They are all in the same plane. So you're going to have to think about your terms from geometry, what you mean by plane. And those angles are going to equal each other. So the light at which it goes in is going to come out at the same angle. When light hits a surface to be reflected off of, the angle that it hits the surface is the angle that it comes off of. Those are equal. And so I think they do a good image here of showing this. You have a ray that hits the surface here. It bounces off at the same surface. So the brain assumes that rays travel in straight lines. So in our brain, we look at a mirror and we assume that it travels in a straight line. So our brain thinks that the image is behind the mirror. This is called a virtual image, And so if you think about when you are facing somebody, your brain hopefully you're saying, oh, well, that's their right and that is their left when you're facing them. It's opposite of what you are. And so when you look in a mirror, your image is directly facing you. And our brain is like, oh, they're behind the mirror looking at me. That's how our brain sees people right in front of us, right? And so that's the virtual image. The virtual image is the image that appears to be behind the mirror looking back at you. That is the definition. It exists in the mind of the observer. It cannot be projected on a screen. Plane mirrors. When considering a mirror image, it's not actually reversed. It's just that our brains see things opposite of us, and we've gotten so accustomed to reversing everything that is looking at us that we look at the mirror and we actually see it. So if two planes are set at right angles and an object is approximately equidistances from each mirror, we see three images. I am sure you have all done this at one time, right? If you have a bathroom that has like a mirror on the side and a mirror here, you know that multiple images are produced, right? If you've ever been in like a fun house at the fair and you see all these mirrors lined up, you see lots of images that happen, right? What happens here is you have equidistance, so you see 1, 2, and then they produce a third one, all right? And then it's going to go on and talk about how you can see like an infinite, which you've ever done that. If you have like held a mirror up in front of a mirror and you can see it basically pinging back and forth, and you can see like it's continually getting smaller of the images. If you've ever done that, right? Where you have a mirror in front of a mirror, and that's what actually happens when they're directly facing each other. So there is a formula, 360, there we go, divided by theta. That's the angle at which they are positioned, minus 1. So if they are directly facing each other, you see an infinite number of images, right? Again, if you've ever been in a fun house where it has two directly across from each other, it looks like the images are continually getting smaller. They're moving towards infinity. But that's why they're continually getting smaller, because the further it goes into that reflection, the further away it looks like they are. Mirrors that have curved surfaces have a variety of applications and interesting characteristics. So in our homes, we probably don't have a lot of curved mirrors, right? We have them on our cars. We see them in stores. In cameras, we have them. We don't usually see that mirror. But if you're in your bathroom, that is a plane mirror. That's what all of those things we just talked about, that is your bathroom mirror, right? And so now we're moving to curved mirrors. And so the first type of mirror we're going to talk about is a concave mirror. Concave mirror. Concave mirror is a mirror formed on the inside of a curved surface, all right? And so if you think about a bowl, if the bowl were facing you and the inside of the bowl has a mirror on it, that is concave, all right? That is concave. The mirror is formed on the inside of a curve. The second type is convex. So flip that bowl around, you're looking at the bottom of the bowl, and the mirror is on the outside there. So it's convex. It comes out towards you, versus concave goes in away from you. These are some terms because we're about to look at an example here. Focus or focal point is the point the reflected rays pass through. Focal length is the distance from the mirror to the focus. The radius of the mirror is the radius of the sphere that the mirror surface is a part of. So if you have a curved mirror, if you were to create the entire sphere that's a part of, the radius of the mirror is the same as the radius of the sphere. So when you have a concave or convex mirror, you only have a portion of an entire sphere. A sphere is like a basketball, an entire sphere. So the radius of the mirror is going to match whatever sphere it would be a part of if you created the entire thing. Principal or optical axis is the line that passes through the center of the spherical surface and the focus. And we're going to look at a picture so that you can see all of these on the image. All right, so let's look at this. This is the formula for it, R/2, which we'll use that later on. We don't need it, but it's there. So you have the actual object. This is the actual object. The radius is going to be, if you were to take this curve and create the entire sphere of this, you would have the radius. All right. And then we have focal point. So we have these reflection lines. So it comes down and off, and you have this where they cross is going to be your focal point. And then this axis is kind of the thing that runs all the way through it. And we're going to look at these things. So when it curves like this, like she said, the inside of a spoon, it's upside down. That would be Y, because you are coming right here, but it's reflecting this way. So then this piece, this top of the head of this knight, which looks like from chess here. So the top of that is hitting here, but now we're not coming off at the same angle. If this were a plane, it would just bounce straight back, right? If there was no curvature at all involved, that image would just come straight back like it does when you're looking in a mirror. But here it comes, because this is angled, the reflection is then angled. And so it hits here, it's going to angle down, and all of a sudden the top of the head is down here. Which means this, so if you took every piece of that, it would create these reflections. So the closer we get to the center, the closer we're going to be at a plane mirror, right? So if we're dead on center, it's going to reflect back, but all of a sudden everything else is down here, right? And so the closer you get to that, you're going to see that angle change. It's not going to be the same angle all the way around, because it's not the same hitting point all the way around. You're at a different point away from it. And that's why it flips when it is concave. It's going to flip it upside down. All right. You'll also notice that the size is affected. That's actually going to be determined by how close or how far away you are. And I'm not going to make you calculate these. There are some calculations you can do to figure out, hey, if I am this size, how far away from the mirror am I? But this is going to be determined by that. And so this is not in your notes here because we're not going to do the calculations, but I wanted to give you kind of the examples. They go through it. We'll talk about this, and then I'll show you the pictures as we go through those examples. A couple rules that concave mirrors follow. The rays, incident rays, meaning the ones that come in are parallel to the principal axis, are reflected through the focus. So if they're parallel, then they're going to come back through the focus. Incident rays that pass through the focus are reflected parallel to the axis. All right. So you're going to have almost, if you can think of it as a transversal running through two parallel lines. You're creating the same angles as if you had two parallel lines and a transversal. And that transversal would be that reflected ray coming off. Two additional rules. Incident rays that pass through the center of the curvature, so this is the center of that curve, are reflected back through it. So just like we saw the base of that knight that looked like he came back at the same angle, it's reflected back through it. Rays that intersect the vertex reflect in according to the law of reflection, and we talked about the law of reflection earlier. So then let's look at this image again right here. We have some terms that go along with this. And this is a sub. So in your handout, this should be a little tiny sub O, the distance of the object to the mirror, and the tiny I is the distance of the image. So the object is the actual thing that's being reflected. The image is the reflection. The image is the reflection. All right. Let's look at these scenarios. How far away they're located. Cases to consider. So, rays are reflected. The image is infinitely small. So if you are basically this is a limit theory for those of you that have had to deal with this in pre-cal, limit theory. The limit theory of this is going to say that as the distance moves towards infinity, the object gets infinitely small. All right, so there's going to come a point where you're not going to be able to see the image in the reflection at all because it's just too far away. Technically, it's still there if the light is able to travel. So if there's nothing blocking you in the mirror, technically it's still there, but it's going to become infinitely small. You're going to just keep moving towards an infinitely small object. The next case, so let's say the distance is larger than the radius. The distance from the object is larger than the actual radius of that curvature. Remember we talked about if we were to take that curve and make an entire circle with it, the radius. Let's say you're further away than the radius. The image is going to be inverted. It's going to be located in between this center and here. So it's going to be smaller and inverted. If it is the same, it's going to be inverted, but it's going to be directly in the same spot. So if they are the same. The distance from the radius is sitting on the radius. They're going to be the same. And then if it's smaller, the image is actually going to be larger and further away. So how far away you are from that curved glass is going to determine what that image does. You'll notice it's always flipped here, but at the same time, it's either closer or further away or right on it, depending on how close to that radius you are. All right. All right, convex mirrors are curved the other way. Remember, this is like the bottom of the bowl and the mirror's on the outside of the bottom of the bowl. The center and the focus are both behind the mirror. There is only one case. You have a virtual image that is upright and reduced. So these will not flip the image. If you are walking in the store and they have a curved glass and someone's walking down the other aisle, they're not going to be upside down from your point of view. All right? Convex mirrors have a variety of applications. Like we mentioned with your mirrors on your car, it says they may be closer than they appear. Well, that's because this looks smaller, right, than it actually is. And so in your brain, if it is smaller, it's further away. Right? That's how vanishing points work. If you've done anything with art or anything else, vanishing points do this. They go further away, they get smaller. And so you see a truck coming up, it's going to look like it's farther away. The problem is that if they made them flat, perfectly flat with no curvature, your vision is not as deep and around. You don't have like if you think about a 360 camera, it sees all the way around. Obviously your mirrors don't, but if it's curved, you're going to see further around. You're going to have fewer blind spots if you're driving, right? If that's just a little bit curved. But at the same time, it could appear that it is smaller. And there, like I said, we're not going to do the math, but there is a direct correlation between how far away you are from either an inner or an outer curve as to where the image is and how small it is, whether it is upright or whether it is reversed. So whether it's concave or whether it's convex, there is going to be a direct correlation with how far away you are from directly radius as to how small that image appears to be. All right, so let's look at a couple other terminology and then we'll be done. Magnification is a factor by which the height of the object is multiplied to determine the height of its image. All right, so what is magnification? We do have a ratio, and we're going to do all of this tomorrow with the formulas. I want you to go ahead and write them down if they're not there. It's a ratio. And then positive distances are in front of the mirror, negative distances are behind the mirror. And this is in when it is curved inward like this. Is that n equals? Obviously, if you say the height of something, you're not going to say a negative height, but you've got to start thinking the direction in which it's reflecting back. Like we mentioned with the spoon, all right? So with a spoon, it's going to look inverted depending on that distance. And so when you see a height that's negative, you're actually just going to think of it as a direction. And then they show us how we come up with these formulas. We're going to get to the actual formulas itself. It says negative signs maintain the correct conventions for concave and convex mirrors. Negative magnification then means that the image is inverted. And so as we calculate some of these things, they're pretty basic calculations. What we're looking for is what does it tell me? So relate it back to like when you graph parabolas. If you saw a negative in front of the parabola, your brain should have immediately said, oh, it flips it, right? And that's kind of the same concept of magnification. Magnification is going to tell you how large it looks compared to the actual image that's there. And it's also going to tell you the direction that it's going to be reflected back to you. So it's just a piece of information based on a positive or a negative. So I gave you the space to write all of this. I'm going to show you how they get to the final one that we're going to use. But basically, they're using similar triangles. It's okay if you don't understand all of the details here. That's fine. You should remember similar triangles. You should remember that you have congruent angles when they are made from intersecting lines. Hopefully you know that. And then if you have similar triangles, they end up creating ratios, all right? And so they are using trig here. You're not going to have to use trig at all in this chapter, but they do use trig to figure out your opposite over your adjacent, just like we would if we used trig of anything, to figure out these ratios that you're going to end up using. Your H's represent your height, your D's represents your distance, and your F represents your focal length. You notice that you have little sub letters. I, well, that is the image versus the object, right? So the object is what is being reflected. The image is the reflection. And so you're going to see those little sub numbers or letters to tell you which one you're talking about. The equation is actually derived. I'm going to use the word derived. Don't get crazy if you do the calculus section, but it's derived down to the basic here. This basic one is what we're going to use the most, and this magnification one is what we're going to use. It wouldn't let me put it like a fraction, so we'll deal with it. But 1 over the distance object, the object of the distance of the object, 1 over the distance of the image. You add those together, and you get 1 over the focal length. All right, this is the one we're going to use most. And then magnification is the height of the image over the height of the object equals the negative distance of the image over the distance of the object. So those are the ones we're going to use. Those two are the ones I have highlighted because that's the ones we're going to use. So 1 over the object, the distance of the object, plus 1 over the distance of the image equals 1 over the focal length. And then your magnification is your height of your image over the height of the object. And that also equals the negative distance of the image over the distance of the object. Couple things just to talk about. So distances, object, image, and focal length. So we're going to use that to find it. If it is positive, that is going to end up in front of the mirror. If it's negative, it's going to end up behind the mirror. The focal length, if the focal length is positive, you have a concave mirror. If it's negative, you have a convex mirror. Your height is always positive. So even if you get a negative height, you're going to tell me the height is positive because we're talking about height. The image can be upright or inverted. So if that height, the image height is positive when you get it, that means it's right side up. If it's negative when you get it, that's inverted. And then magnification, if it's positive, it's upright. And virtual means it's in front of the mirror. If it's negative, it's going to be inverted or upside down. It can be enlarged or reduced. So if your magnification is bigger than 1, then the image is going to look bigger. If it's less than 1, it's going to look smaller. So that's how we're going to interpret these as we do these problems. So let's look at this first one. We're going to label some of these. So it says a 1.75 centimeter object. What they just gave us right here was the height of the object. Height of the object is 10.0 centimeters from a concave mirror. Here, they have given us the focal length. 10 centimeters, that's your distance. Sorry, not focal length. This guy is your distance of the object. Then we're going to get to focal length. And then they actually told us focal length is 20. All right, so we have those right there. Object's height, object's distance, and the focal length. All right, so the equation that we're going to use is the 1 over the focal length equals 1 over the object's distance plus 1 over the image distance. Because the first thing they want to know is position of the image. They want to know where is the image when you look at it. Where does it look to be? And so we're going to plug this in and we're going to use just basic fraction, common denominator, easy stuff, all right? So 1 over my focal length, that's going to be 1 over that 20 centimeters. That is going to equal, we don't need the height of the object right now. We'll use that in a minute. But that is going to equal the distance. So we're going to say 1 over the distance of the object added to 1 over the distance of the image, which is what we're trying to find. Basic fractions. Basic solving. I'm solving for that variable. I need to subtract anything that is not with that variable. So I'm going to subtract that 1 over 10 to the other side. 1 over 20 minus 1 over 10 equals 1 over the distance of the image. What do I need to add those? I cannot flip everything. So that little trick of flipping both sides only works if you have ratios. 1 fraction equal to 1 fraction. You can't do that right now, right? What you have to do right now is get a common denominator, a pretty simple one. What is my common denominator between 10 and 20? 20. So we're going to make this 2 over 20, right? You have to go up. 2 over 20. Position. In the numerator position, we have 1 minus 2, negative 1. In the denominator, we still have that 20. Now that we have this, we can flip them, and we know the distance of the image. What is the distance of that image? It's right there. Just flip both sides. Now we can flip both sides. So the distance of the image, A, is going to be negative 20 centimeters. Negative 20 centimeters. All right. All right, the next question says, determine the height of the image. All right, height of the image. So for height of the image, we're going to use, for this one, we're going to go ahead and jump, and I'm going to go ahead and jump and do magnification. So it says determine the magnification. Well, my magnification is a couple things. We can say magnification can use our heights, which is what we're going to actually eventually solve for. And then it also can use our distances. So our height of, or our distance over our distance is what's going to help us. So we have the distance of our image over our original distance of our height. The negation of that is going to equal the height over the height. And so we're going to take that distance over distance and negate it, and then back into the height using that. All right, so the first thing we're going to find here is our magnification. We know the distance of the image. We just found that. That is negative 20. This already has a negative in front of it. Just pay attention to that. And we know the distance of the object that was given to us originally is 10. So the magnification here is negative 20 over 10, which is just negative 2, and then negate it because there was already a negative in front of it. Our magnification is 2. All right, so we're going to now use that to back into our height. We found our magnification to back into our height. That also equals the height of our image, which we still don't know yet, over the original height. Now we need that 1.75. That is our original height of our object, 1.75. So we're actually solving for B here using this. We're going to go back up. We found our distance of our image. We found our magnification of our image. When you multiply that 1.75 over, you get your height of your image. They just asked it in a different order than it was easy to solve for. So we have the 3 things they've asked for prior to describing it. We have position of the image, negative 20. We have height of the image, 3.5 centimeters. And we have magnification of the image, which is 2. So then they tell us to describe it. So this is where that chart helps, all right? We have a negative distance, The negative distance tells us that this object is behind the reflection. The negative distance tells us it's behind the reflection there. Then we have a height of 3.5. Remember I said your height will always technically be positive. In this case, it was positive, but you could get a negative answer, right? We got a positive answer. You will always list it as positive, but even originally when we did it, we got positive. 2 times 1.75 is a positive number. So a positive height, so the positive height tells us that this is upright, not flipped. So a positive height is going to tell us this guy is upright. Same direction. Had we originally gotten a negative height, we would have said, hey, the height is 3.5, but the negative that we got when we multiplied tells us it's flipped, which we're going to do one similar. All right. So we now know he's behind the mirror or whatever it's being reflected off of. We know that it is upright, and then the magnification is greater than 2. So the magnification tells us, because it's greater than 1, which 2 is greater than 1, this tells it is larger. Now, so does logic. Larger than the object. What else tells us it's larger than the object? Well, the height, right? But the magnification greater than 1 tells us that that image is larger than the object itself. It's going to appear larger behind that mirror and upright. Same orientation. The position. I'm going to say my focal length. So you want to label these. Focal length, right, is there. Height of the object is here. Distance of the object is there. So my focal length, we're going to say 1 over my focal length equals 1 over my distance of my object plus 1 over my distance of my image. Do exactly the same thing. We're going to subtract that over. We're going to get a common denominator. Minus 1 over 10 equals 1 over my distance. Multiply your 1/5 by 2, you get 2/5. 2/5 minus 1, you get, or 2/10 minus 1/10, you get 1/10, and flip it over, you get 10. So my distance here is 10 centimeters. Distance here is 10 centimeters. That is A. I'm going to skip B for right now. I don't know why they give it to me in that order. We're going to go straight to my magnification. And then we'll deal with the height. Remember, my magnification, I'm going to use a negative and use my 2 distances. The distance of my object the distance of my image over the distance of my object, and negate it. So -1 is my magnification. -1 is my magnification. And then we're going to use that magnification with our heights. The height of our image that we don't know over the height of our object that we do know. Multiply it across. The height of the object is -5 centimeters. What does this tell us? All right. So the first thing that it tells us is this distance is positive. Remember, a positive distance means that it is in front. It appears in front, right? And they would call this a real image. So this is in front here. -5. How am I going to write the actual height for my answer? What would my answer be to say what the height is? 5. We would say +5 is my actual height. But when I calculated it, it was negative, right? It was negative. So how is it going to appear if it was originally negative? It's going to be inverted, right? So this is going to appear inverted. So we're going to say inverted, upside down, however you want to write that. But that's what that tells us, inverted. All right? And then what does the magnification tell us here? Look at our magnification here. Yeah, the magnification is -1, which, I mean, when you multiply it out, it's just telling you, again, a distance, when you look at absolute value of how it changed, it's not going to affect the height if you multiply it, right? So when we multiplied it, the only thing it did to the height is tell us it was inverted. It's actually going to be the same size, right? When you look at magnification, you're looking at the absolute value of it. The negative is just helping you decide if it's going to be upside down or right side up when you multiply it over to the height. So your magnification is still a 1. It's going to be the same size. It's going to be the same size, just upside down. Spherical aberration. It's the phenomenon where incident rays strike a distance away from the vertex of a spherical mirror or lens, causing a slight deviation of reflected or refracted rays from the focus. We'll talk about this. I'll give you a second to write it down. So what happens with spherical aberration is, as you can imagine, the image can be skewed, as you have all seen in like a curved mirror if you have looked at, a house of mirrors. Different part of the mirrors, the light hits different sections, And so it focuses differently at different points. And so if they hit the center of the mirror, it's going to go to one spot. If it hits the edge of the mirror, it's going to come off at a different spot. And you can sometimes get blurry or a fuzzy image, which is where we use the word aberration anyway. But the spherical aberration just causes those to come off at different points, unlike a flat image. And so that term, spherical aberration, is what happens. So if you design a mirror on the basis of a parabola instead of a sphere, it actually removes the aberration. You actually have them all reflect back to a single focal point. This comes from our same parabola concept of your axis of symmetry. When we study satellites, right? They all come back to that focal point in a satellite, which is what helps us do it. So a parabola mirror reflects every incident light ray parallel to the optical axis through the principal focus. And so it all ends up being parallel if you do a parabola. They have definite centers of curvature and indefinite focal points when it is spherical. Spherical mirrors have definite centers of curvature and indefinite focal points, depending on where it's going to hit it. Parabola mirrors have indefinite centers of curvature and distinct focal points. Distinct focal points between those. So a sphere versus parabola is going to produce different things. This is not in your handout, but we talked about this. Our brains are the ones that tell us things are flipped because we are so used to looking at things directly on and knowing that it is opposite of what we are. And so if you can take a plastic bag, draw an arrow on the plastic bag, and hold it up to a mirror, and you will see it is the same direction that you were looking at, right? But when you see it in the mirror, your brain thinks that image is holding it and thinks it's holding it a different direction, right? But you can see through. If you reflect something that has an image on it that you can see through, you will see the image in the same orientation that you have it.